We have journeyed to the realm before the Big Bang, to that timeless void where even nothingness held no meaning. We explored the quantum foam, the false vacuum, the eternal cycles. We asked what existed before time itself. Now we stand at the threshold, the transition point, the moment when potentiality becomes actuality, when the timeless gives birth to time, when nothing becomes everything. This is the story of the first moments after the Big Bang. Not the Big Bang itself. That singular event remains shrouded in mystery, perhaps forever beyond our complete understanding. But what came immediately after, in those first unimaginably brief fractions of a second, we can describe with mathematics and physics. These are the moments when time began to tick, when space began to expand, when energy condensed into the first particles, when the laws of physics as we know them activated and began shaping reality. The story we are about to tell spans less than a second. Yet, in that first second, more happened than in all the billions of years that followed. The universe transformed from a state beyond description into something recognizable, something that would eventually give rise to stars, galaxies, planets, and life. Close your eyes. Breathe slowly. Imagine standing at the very edge of time itself, watching as existence explodes into being. This is the birth of time. This is where our universe truly begins. The journey starts now at the Planck Epoch, the earliest moment we can meaningfully describe. The Planck Epoch, the first 10 to the minus 43 seconds of cosmic history. This is the Planck time, the smallest meaningful unit of time in physics. Nothing that happens faster than this can be measured or even defined by our current understanding. At this moment, the universe is unimaginably small, unimaginably hot, unimaginably dense. All the energy that will eventually become the observable universe, hundreds of billions of galaxies, each with hundreds of billions of stars, is compressed into a region smaller than a proton. The temperature is 10 to the 32 Kelvin. There is no comparison in our everyday experience for such heat. The core of the sun is 15 million Kelvin. The center of a nuclear explosion is billions of Kelvin. This is trillions of times hotter. At such temperatures, at such densities, the four fundamental forces we know today, gravity, electromagnetism, strong nuclear force, weak nuclear force, are unified into a single superforce. There is no distinction between them. They are one. Matter as we know it cannot exist. Particles as we know them cannot exist. Even space and time themselves are quantum, fluctuating, uncertain. The smooth fabric of space-time breaks down into quantum foam at these scales. Our equations, our physics, our understanding reaches its limit here. General relativity cannot describe gravity at such scales. Quantum mechanics cannot describe space-time. We need a theory of quantum gravity, string theory, loop quantum gravity, something we haven't discovered yet. But we can say this: at the Planck Epoch, the universe exists in a state utterly alien to anything we experience or can fully comprehend. As the universe expands and cools, and this happens astonishingly fast, the first transformation occurs. At 10 to the minus 43 seconds after the Big Bang, we cannot describe physics. But by 10 to the minus 36 seconds, we can begin to apply our theories. The temperature has dropped to 10 to the 27 Kelvin. Still unimaginably hot, but cooler than the Planck Epoch. And in this cooling, something profound happens. The unified superforce begins to separate. First, gravity splits off. It becomes distinct from the other forces. This is the moment when space-time becomes classical, when the geometry of space becomes definite rather than quantum. Gravity, the curvature of space-time, now operates according to Einstein's general relativity. The other three forces, electromagnetism, strong nuclear, weak nuclear, remain unified in what physicists call the electronuclear force or the grand unified force. This is the era of grand unification, the GUT era. In this era, particles and antiparticles form and annihilate constantly. Quarks and leptons are interchangeable. There is a beautiful symmetry to physics at this energy scale, a simplicity that will be broken as the universe continues to cool. The universe is still incredibly small, perhaps the size of a grapefruit, perhaps smaller, depending on how much inflation has occurred. But it contains all the energy of our future cosmos, seething with particle-antiparticle pairs, governed by unified forces, expanding exponentially. This grand unification epoch lasts until about 10 to the minus 32 seconds. Then another transition occurs. At approximately 10 to the minus 36 seconds, the universe undergoes the most dramatic transformation in its history. This is the beginning of cosmic inflation, a period of exponentially rapid expansion that will shape everything we observe today. The inflaton field, which we discussed in our journey before the Big Bang, is still in a false vacuum state. It has energy, but this energy is not yet in the form of particles and radiation. Its potential energy, stored in the field itself. As the inflaton field begins to roll down from its false vacuum state toward the true vacuum, its energy drives inflation. Space itself expands faster than light. This doesn't violate relativity. Nothing is moving through space faster than light. Space itself is expanding, carrying everything with it. How fast is this expansion? In a fraction of a second, perhaps 10 to the minus 32 seconds, the universe expands by a factor of at least 10 to the 26. A region smaller than an atom becomes larger than our observable universe today. This is hard to visualize. Imagine a single bacterium expanding to the size of the Milky Way galaxy in less time than it takes light to cross a proton. This gives you a sense of the scale, though even this analogy falls short. Why does inflation happen? The inflaton field's energy has a peculiar property. It creates negative pressure. This negative pressure drives expansion. The more space expands, the more inflaton field there is, the more negative pressure, the faster the expansion. It's a runaway process. For a brief moment, inflation dominates everything. During inflation, something remarkable happens that will determine the structure of the universe billions of years in the future. Quantum fluctuations in the inflaton field get stretched to cosmic scales. At the quantum level, everything fluctuates. The inflaton field has a value at each point in space, but this value is not perfectly uniform. Quantum uncertainty means there are tiny random variations. Here the field is slightly higher in energy, they're slightly lower. Normally, these quantum fluctuations are microscopic, far too small to affect anything at human or even atomic scales. But during inflation, space expands so rapidly that these tiny fluctuations get stretched. Regions that were separated by less than the Planck length suddenly find themselves separated by light years, then by millions of light years. The quantum fluctuations become cosmic fluctuations. Regions where the inflaton field was slightly denser will eventually become regions where matter clusters more densely. Regions where it was slightly less dense will become voids. These tiny variations, differences of only 1 part in 100,000, are the seeds of all cosmic structure. They will eventually grow under gravity into galaxies, clusters of galaxies, and the vast cosmic web we observe today. This is one of the most beautiful predictions of inflation theory. Random quantum events at the smallest possible scales get amplified to cosmic scales, and we can observe their effects billions of years later in the pattern of galaxies across the sky and in the cosmic microwave background radiation. The quantum and the cosmic are connected. inflation cannot last forever. The inflaton field is rolling down from the false vacuum toward the true vacuum, and eventually it reaches the bottom. When it does, inflation ends as suddenly as it began. This happens at approximately 10 to the minus 32 seconds after the Big Bang. The inflaton field reaches the true vacuum and begins to oscillate around this minimum energy state, like a ball rolling into a valley and bouncing back and forth at the bottom. As the inflaton field oscillates, it decays. Its energy converts into particles and radiation. This process is called reheating because the universe, which had cooled during inflation, suddenly heats up again as the inflaton's energy becomes kinetic energy of particles. The temperature soars back to perhaps 10 to the 27 Kelvin or higher, though not as high as the Planck Epoch. The universe fills with a hot, dense soup of fundamental particles. Quarks, leptons, photons, and others will explore. The exponential expansion of inflation stops. The universe continues to expand, but now at a much slower rate, governed by the normal expansion of spacetime filled with matter and radiation, rather than by the peculiar properties of the inflaton field. The universe has grown from subatomic size to perhaps the size of our solar system or larger, depending on exactly how long inflation lasted. All of this in a tiny fraction of a second. And now, filled with energy in the form of particles, the universe begins its more familiar evolution. The stage is set for matter as we know it to form. We have traveled through the first microsecond of cosmic time. In that unimaginably brief span, the universe transformed from a state beyond description, unified forces, quantum spacetime, infinite temperature, into something almost recognizable. Quarks have bound into protons and neutrons. The four fundamental forces are distinct. The laws of physics as we know them are in effect. Now, as we approach the end of the first full second of cosmic history, the universe continues to cool and expand. The temperature is dropping, but it's still around 10 billion Kelvin, nearly 1,000 times hotter than the core of our sun. The density is immense, far greater than the densest matter we can create on Earth. The universe at this moment is filled with a seething plasma. Protons and neutrons collide constantly, sometimes sticking together briefly before being torn apart by energetic photons. Electrons and positrons still exist in roughly equal numbers, constantly annihilating and being recreated from high-energy photons. Neutrinos, those ghostly particles that barely interact with anything, are finally decoupling from the rest of matter. In the denser, hotter early moments, even neutrinos interacted frequently with other particles. But now, as density drops, neutrinos begin to travel freely through the universe. They will continue traveling, mostly undisturbed, for the rest of cosmic history. The cosmic neutrino background created in this moment still fills the universe today, though we've never detected it directly. The balance between protons and neutrons is shifting. In the hottest moments, protons and neutrons could convert freely into each other through weak force interactions. But as the universe cools, these conversions slow down. As the universe continues to expand and cool after inflation, at around 10 to the minus 12 seconds, another critical transition occurs. The temperature has dropped to about 10 to the 15 Kelvin, and the electroweak force separates. Remember, after gravity split off during the Planck Epoch, three forces remained unified: electromagnetism, the weak nuclear force, and the strong nuclear force. During the GUT era, the strong force separated. Now, electromagnetism and the weak nuclear force separate from each other. This separation is driven by something called spontaneous symmetry breaking. The universe, in its hot early state, had a symmetry, electromagnetism, and the weak force were indistinguishable. But as it cooled below a critical temperature, This symmetry spontaneously broke, like water freezing into ice crystals that pick a particular orientation. The agent of this symmetry breaking is the Higgs field. Yes, the same Higgs field that gives particles mass, the field whose quantum is the Higgs boson discovered at CERN in 2012. In the hot early universe, the Higgs field was in a symmetric state with zero value. As the universe cooled, the Higgs field suddenly acquired a non-zero value everywhere in space. This non-zero Higgs field value has profound consequences. It gives mass to the W and Z bosons, the carriers of the weak force. It gives mass to quarks and leptons. Suddenly, particles that were massless become massive. The weak force becomes short-range. Electromagnetism remains long-range. The four fundamental forces we know today, gravity, electromagnetism, strong, weak, are now distinct and separate. After the Electroweak transition, the universe is filled with a hot plasma of fundamental particles. We're now at about 10 to the minus 6 seconds after the Big Bang, and the temperature is around 10 to the 13 Kelvin. At these temperatures, quarks exist freely. Quarks are the fundamental constituents of protons and neutrons, but in our everyday world, quarks are never found alone. They're always bound together in groups. 3 quarks make a proton or neutron, a quark and an antiquark make a meson. But in the early universe, it's so hot that quarks can't bind together. The thermal energy is too great. Quarks and antiquarks swim freely in a sea of gluons, the particles that carry the strong force. This state of matter is called a quark-gluon plasma. It's a soup of the most fundamental constituents of matter, unbound, free-moving, interacting constantly. We've never seen this in nature under ordinary conditions, but physicists have recreated it briefly in particle accelerators by colliding heavy nuclei at enormous energies. The quark-gluon plasma is incredibly dense and hot. Quarks and antiquarks are constantly being created from energy and annihilating back into energy. Gluons mediate the strong force between quarks. The plasma glows with high-energy photons. This is a symmetric state. For every quark, there's an antiquark. For every particle, an antiparticle. Matter and antimatter exist in equal amounts, constantly transforming into each other through particle-antiparticle creation and annihilation. But this balance is about to be broken in one of the most important asymmetries in cosmic history. At some point during the Quark Epoch, probably around 10 to the minus 6 seconds, something broke the symmetry between matter and antimatter. This is one of the greatest mysteries in physics, and one of the most crucial events in cosmic history. In the hot early universe, matter and antimatter were created in equal amounts. For every quark, an antiquark. For every electron, a positron. When a particle meets its antiparticle, they annihilate, converting their mass entirely into energy, into photons. If matter and antimatter had remained perfectly balanced, everything would have annihilated. The universe would contain only photons, no matter at all. There would be no atoms, no molecules, no stars, no planets, no life. Just light in an expanding void. But somehow there was a slight imbalance. For every billion antiquarks, there were 1,000,000,001 quarks. This tiny asymmetry, 1 part in 1,000,000,000, meant that when the matter-antimatter annihilation was complete, a small residue of matter remained. That residue is everything we see. Every star, every galaxy, every atom in your body exists because of this 1 part in 1,000,000,000 asymmetry between matter and antimatter in the early universe. Why did this asymmetry exist? We don't know for certain. The Russian physicist Andrei Sakharov identified 3 conditions necessary for such an asymmetry to arise: baryon number violation, C and CP symmetry violation, and departure from thermal equilibrium. Experiments have confirmed some of these mechanisms exist, but the full explanation remains elusive. What we do know is that without this asymmetry, we wouldn't exist. As the universe continues to expand and cool, at about 1 microsecond after the Big Bang, the temperature drops below 10 to the 13 Kelvin. This is cool enough for quarks to bind together permanently. The quark-gluon plasma undergoes a phase transition, like water freezing into ice. Suddenly, quarks can no longer exist freely. The strong force binds them together into hadrons, particles made of quarks. 3 quarks bind together to form baryons. The most important baryons are protons and neutrons. A proton consists of 2 up quarks and 1 down quark. A neutron consists of 1 up quark and 2 down quarks. These are the building blocks of atomic nuclei. Quark-antiquark pairs bind together to form mesons. Mesons are unstable and quickly decay, but they play important roles in mediating forces between baryons. This transition from free quarks to bound hadrons is called the QCD phase transition, named after quantum chromodynamics, the theory of the strong force. It's one of the most important phase transitions in cosmic history. The universe is now filled with a hot plasma of protons, neutrons, electrons, positrons, neutrinos, and photons, all interacting intensely. The temperature is still far too high for atomic nuclei to form. Any nucleus that formed would immediately be blasted apart by high-energy photons. But the stage is set. The quarks are confined. The fundamental particles of matter as we know it now exist. In the next moments, these particles will begin their journey toward forming the first atomic nuclei, the first step toward atoms, molecules, and eventually life. After recombination, the universe goes dark. Not completely, the cosmic microwave background fills space with radiation, and this radiation is initially in the visible and infrared range. But within a few million years, cosmic expansion stretches these photons into the infrared and then into microwaves. Visible light becomes scarce. More importantly, there are no light sources. Stars have not yet formed. Galaxies do not exist. There are no quasars, no supernovae, no glowing nebulae. The universe contains only neutral hydrogen and helium gas, slowly clumping under gravity, and the fading afterglow of the Big Bang. This period is called the Cosmic Dark Ages. It lasts from recombination at 380,000 years until the first stars ignite, somewhere between 100 million and 400 million years after the Big Bang. During this time, the universe is truly dark and quiet, a vast expanse of cooling gas with no light sources to illuminate it. Yet even in darkness, structure is forming. Dark matter, which makes up about 85% of all matter but doesn't interact with light, has been clumping under gravity since recombination. Actually, dark matter began clumping even earlier. It never coupled to radiation, so it wasn't held back by radiation pressure. While ordinary matter was stuck in the plasma, dark matter was already forming the gravitational wells that would eventually host galaxies. By the time recombination occurs, dark matter has created a cosmic web, a network of filaments and nodes where density is higher than average. Ordinary matter, newly freed from radiation, begins falling into these dark matter structures. Gas flows along filaments, accumulating in the densest regions, where the first stars will eventually form. Neutrons are slightly heavier than protons, about 0.1% more massive. This tiny mass difference seems insignificant, but in the cooling universe, it becomes crucial. As the temperature drops below the energy equivalent of this mass difference, neutrons become disadvantaged. The weak force allows protons to turn into neutrons and vice versa through processes involving electrons, positrons, and neutrinos. But converting a lighter proton into a heavier neutron requires energy input from the environment. Converting a heavier neutron into a lighter proton releases energy. As the universe cools, there's less energy available to create neutrons, so neutrons begin to decay into protons. By the end of the first second, the ratio has shifted dramatically. For every neutron, there are now about 6 protons. This ratio will have profound implications for the chemistry of the universe. If there were equal numbers of protons and neutrons, most would bind into heavy elements. If there were almost no neutrons, only hydrogen would form. The actual ratio, roughly 6 to 1, will produce a universe that's mostly hydrogen with a significant amount of helium and trace amounts of other light elements. Free neutrons are unstable. Left alone, a neutron will decay into a proton, electron, and antineutrino with a half-life of about 10 minutes. In the hot early universe, collisions were so frequent that neutrons didn't have time to decay. They were constantly being created and destroyed through interactions. But as the universe expands and density drops, isolated neutrons begin to decay. The clock is ticking. If these neutrons don't bind into stable nuclei soon, they'll all decay into protons, and the opportunity to form helium and other elements will be lost. For 3 minutes, nothing much happens, at least nothing permanent. The universe continues to expand and cool. The temperature drops from billions to hundreds of millions of degrees. Protons and neutrons collide, occasionally sticking together to form deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. But these deuterium nuclei don't survive. The universe is still filled with high-energy photons, and these photons have enough energy to blast deuterium nuclei apart as soon as they form. This is called the deuterium bottleneck. Until the universe cools enough that photons can no longer destroy deuterium, nuclear fusion cannot proceed. Deuterium is crucial because it's the first step in building heavier elements. 2 protons alone won't stick together. They repel each other through electromagnetic force. But a proton and neutron can bind into deuterium, and deuterium can then fuse with other protons or neutrons to build helium-3, tritium, and eventually helium-4. Around 3 minutes after the Big Bang, the temperature drops below 100 million Kelvin. This is still incredibly hot, hotter than the core of any star, but it's cool enough. The deuterium bottleneck breaks. Suddenly, deuterium nuclei can survive, and nuclear fusion begins in earnest. This is Big Bang nucleosynthesis, the process that will determine the chemical composition of the universe for billions of years to come. The universe has become one enormous fusion reactor, converting protons and neutrons into helium and trace amounts of lithium and beryllium. This process will last only a few minutes, but its consequences are eternal. The helium created in these moments will still exist in stars and planets billions of years later. Once deuterium can survive, fusion proceeds rapidly. Deuterium nuclei collide with protons to form helium-3, 2 protons and 1 neutron. They collide with neutrons to form tritium, 1 proton and 2 neutrons. Helium-3 and tritium then fuse together, or tritium fuses with deuterium to form helium-4, 2 protons and 2 neutrons. Helium-4 is remarkably stable. It's the end point of Big Bang nucleosynthesis for almost all the matter in the universe. The binding energy holding its 4 nucleons together is greater than any other light nucleus. Once formed, helium-4 nuclei persist. The process is extraordinarily efficient. Nearly all the remaining neutrons end up locked in helium-4 nuclei. Since the neutron-to-proton ratio was about 1:6 at the start of nucleosynthesis, and helium-4 contains equal numbers of protons and neutrons, about 25% of the universe's ordinary matter by mass becomes helium. The remaining 75% stays as hydrogen, single protons that never found neutrons to bind with. Tiny amounts of other elements form. Some deuterium survives without fusing further. A small amount of helium-3 remains. Trace amounts of lithium-7 and beryllium-7 form through more complex reactions. But these are rare, measured in parts per billion. Nothing heavier than lithium forms in significant quantities. The universe is expanding and cooling too rapidly. By the time helium-4 is abundant, the temperature has dropped below what's needed to fuse helium into carbon or oxygen. There's also a gap. No stable nucleus exists with 5 or 8 nucleons. So building from helium-4 to heavier elements requires rare three-body collisions that don't happen often enough in the rapidly expanding early universe. By 20 minutes after the Big Bang, it's over. The temperature has dropped below 10 million Kelvin. Nuclear fusion stops. The universe has settled into its primordial chemical composition. Roughly 75% hydrogen by mass, 25% helium, and trace amounts of deuterium, helium-3, and lithium. This composition will remain essentially unchanged for hundreds of millions of years, until the first stars form and begin their own fusion processes. The helium created in these first 20 minutes is called primordial helium, to distinguish it from helium created later in stars. When we observe distant galaxies and measure their helium abundance, we're seeing the echo of these first moments, the signature of Big Bang nucleosynthesis. This is one of the great triumphs of Big Bang cosmology. In the 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman calculated what elements should form in a hot Big Bang. They predicted roughly 25% helium, exactly what we observe. When astronomers measured the helium abundance in old, metal-poor stars and in distant galaxies, they found the predicted ratio. This agreement between theory and observation, accurate to within a few percent, is powerful evidence that the Big Bang theory is correct. The neutrons that didn't get incorporated into helium nuclei have decayed by now. Free neutrons have a half-life of about 10 minutes, and 20 minutes is 2 half-lives. Any neutron that remained isolated has become a proton, electron, and antineutrino. The window for building helium has closed permanently. The primordial composition is set, frozen into the expanding, cooling universe, waiting for stars to be born and forge heavier elements. The universe at 20 minutes old is still unimaginably hot and dense by our standards, though vastly cooler and more diffuse than it was at 1 second. The temperature is around 10 million Kelvin. Atomic nuclei exist, hydrogen and helium nuclei mostly, but atoms do not. Any electron that tries to bind to a nucleus is immediately knocked free by an energetic photon. The universe is ionized, a plasma of nuclei and free electrons. This plasma is opaque to light. Photons cannot travel far before interacting with an electron, scattering in a new direction. Imagine trying to see through a thick fog. Light scatters off water droplets, diffusing in all directions, preventing you from seeing clearly. The early universe is like this, but instead of water droplets, photons scatter off free electrons. The universe is filled with light, but the light cannot travel freely. It bounces from electron to electron in a random walk, trapped in the hot plasma. Matter and radiation are tightly coupled. The pressure of radiation pushes on matter. The gravity of matter pulls on radiation. They exchange energy constantly. A high-energy photon strikes an electron, transferring momentum. An electron accelerates and emits photons. Everything is in thermal equilibrium, matter and radiation at the same temperature, energy flowing back and forth between them. This coupling between matter and radiation has important consequences. Small density fluctuations, those quantum seeds stretched to cosmic scales during inflation, try to collapse under their own gravity. But radiation pressure pushes back, preventing collapse. The fluctuations oscillate, growing and shrinking like sound waves. These are called baryon acoustic oscillations, and we can still detect their imprint in the distribution of galaxies today. After the drama of the first 20 minutes, inflation, particle creation, matter-antimatter annihilation, nucleosynthesis, the universe enters a quieter phase. The temperature continues to drop, but no new transformations occur. The universe simply expands and cools, following the equations of general relativity and thermodynamics. This phase lasts for hundreds of thousands of years. Nothing much happens, at least nothing visible or dramatic. The plasma continues its random dance of photons and electrons. Nuclei drift through the ionized fog. Neutrinos, now completely decoupled, stream freely through space. Dark matter, which doesn't interact with photons at all, begins to clump under gravity, forming the scaffolding on which galaxies will eventually assemble. The universe is still uniform to an extraordinary degree. The density varies from place to place by only 1 part in 100,000. To an observer anywhere in this universe, if observers could exist in such conditions, it would appear essentially the same in all directions. A featureless, glowing fog extending to infinity. But those tiny variations matter. In regions slightly denser than average, gravity is slightly stronger. Matter wants to clump together, but it cannot, not yet. The radiation pressure is too strong. Photons push on electrons, electrons drag on nuclei through electromagnetic forces, and the whole plasma resists gravitational collapse. The universe is in a state of tension. Gravity pulls inward. Radiation pressure pushes outward. These forces balance, creating oscillations in the plasma density. The universe rings like a bell struck at the moment of the Big Bang, with sound waves propagating through the plasma at nearly half the speed of light. These oscillations are too large to perceive, wavelengths of millions of light years, but they're there, waiting to leave their mark. During this long, quiet epoch, radiation dominates the universe. What does this mean? In Einstein's general relativity, both matter and radiation have gravity. Both curve spacetime. Both affect cosmic expansion, but they affect it differently. Matter's density decreases as the universe expands. If you double the universe's size, the same amount of matter occupies 8 times the volume, so density drops by a factor of 8. This is simple geometry, but radiation's energy density decreases faster. Not only does radiation spread out as the universe expands, but each photon also loses energy as its wavelength stretches. Double the universe's size, and photon density drops by a factor of 8, while each photon's energy drops by a factor of 2. Total radiation energy density drops by a factor of 16. In the early universe, radiation's energy density is much higher than matter's. The universe is filled with energetic photons, gamma rays, X-rays, carrying far more energy than the relatively slow-moving particles of matter. So radiation's gravity dominates. The expansion of the universe is controlled by radiation, not matter. But as the universe expands, radiation's energy density drops faster than matter's. Eventually, matter must take over. This transition happens around 50,000 years after the Big Bang. Before this moment, radiation dominates and drives expansion. After this moment, matter dominates. This transition has consequences for structure formation. Those density fluctuations, those seeds of future galaxies, behave differently in a radiation-dominated universe than in a matter-dominated one. The transition from radiation to matter dominance allows gravity to finally begin pulling matter together more effectively, setting the stage for the formation of the first structures. As the universe continues to expand and cool, approaching 380,000 years after the Big Bang, the temperature drops toward 3,000 Kelvin. This is a critical threshold. At temperatures above 3,000 Kelvin, hydrogen remains ionized. Below this temperature, electrons can bind to protons to form neutral hydrogen atoms without being immediately blasted free by photons. The transition is not instantaneous. As the temperature approaches 3,000 Kelvin, electrons begin to bind to nuclei in increasing numbers. At first, these newly formed atoms are quickly reionized by energetic photons. But as the temperature drops further, the photons have less and less energy. Fewer and fewer photons have enough energy to ionize hydrogen atoms. The balance shifts. More atoms form than are destroyed. The ionization fraction, the percentage of hydrogen that remains ionized, begins to drop rapidly. At 3,000 Kelvin, perhaps half the hydrogen is neutral. As the temperature falls to 2,900 Kelvin, then 2,800, the ionization fraction plummets. This process is called recombination, though it's a misleading name. The electrons have never been combined with nuclei before. They've been free since the Big Bang. But the term stuck, inherited from atomic physics where electrons recombine with ions after being stripped away. Recombination is one of the most important events in cosmic history. When electrons bind to nuclei, when the universe transitions from ionized plasma to neutral gas, photons suddenly can travel freely. The fog clears. Light, which has been trapped in a random walk through the plasma for hundreds of thousands of years, is released. The universe becomes transparent. The moment of recombination creates what astronomers call the surface of last scattering or the cosmic photosphere. Before this moment, photons scatter constantly off free electrons. After this moment, photons travel unimpeded through neutral gas. The boundary between these two states is the last surface from which photons scattered before traveling freely to us. This surface exists everywhere in space at a specific time, 380,000 years after the Big Bang. When we look out into the universe with telescopes, we see galaxies at various distances and times. Nearby galaxies appear as they were millions of years ago. Distant galaxies appear as they were billions of years ago. The farther we look, the farther back in time we see. But we cannot see beyond recombination. Beyond that moment, the universe is opaque. Any photon that last scattered before recombination scattered many more times afterward, losing all information about its original direction. The cosmic photosphere is the ultimate limit of optical observation. We cannot see through it to earlier times. However, the photons that last scattered at recombination are still reaching us today. They've been traveling through space for over 13 billion years. Their wavelengths stretched by cosmic expansion from visible and infrared light into microwaves. We detect them as the cosmic microwave background radiation, a faint glow filling the entire sky with a temperature of 2.7 Kelvin. This radiation is the oldest light in the universe. It carries information about conditions at recombination, the temperature, density, and distribution of matter at that time. Tiny variations in this radiation's temperature from place to place reflect those primordial density fluctuations, those quantum seeds from inflation, now visible as temperature differences of a few parts in 100,000. At the moment of recombination, the universe undergoes a profound transformation. For 380,000 years, matter and radiation have been locked together in intimate embrace. Photons scatter off electrons millions of times per second. Energy flows constantly between radiation and matter, keeping them at the same temperature. They move together, breathe together, exist as a unified plasma. Now suddenly this coupling breaks. Electrons bind to nuclei. Free electrons, which photons scatter from, nearly disappear. The mean free path of a photon, the average distance it can travel before hitting an electron, increases from microscopic scales to effectively infinite. Photons that were trapped in the plasma for hundreds of thousands of years are suddenly free. These photons begin their journey across the cosmos. They travel through the expanding universe, their wavelength stretching as space expands, their energy decreasing, but their number staying constant. The universe has approximately 1 billion photons for every proton, a ratio set in the early moments after the Big Bang. These photons fill space uniformly, creating a bath of radiation that will persist forever. Matter, meanwhile, is on its own for the first time. Without radiation pressure supporting it, matter can finally respond purely to gravity. Those small density fluctuations, held back by radiation pressure for hundreds of thousands of years, can now begin to collapse. Regions slightly denser than average can pull in surrounding matter. The seeds of structure can finally begin to grow. The universe has crossed a threshold. Behind lies the opaque plasma of the photon epoch. Ahead lies the transparent neutral gas of the matter epoch. Structure formation can finally begin in earnest. As we conclude this journey through the birth of time, we return to wonder, the wonder that drives all inquiry, all exploration, all seeking of understanding. Why does time exist? Why does anything exist? These questions may never have final answers, but asking them shapes us. Time began in an instant of transformation, when the timeless became temporal, when potential became actual, when nothing or something beyond our understanding became everything. In that first fraction of a second, all the energy that would become stars and galaxies and planets and life came into being. The universe expanded, cooled, evolved, organized itself into structures of breathtaking intricacy. Against all odds, against the tendency of entropy to disorder, gravity pulled matter together. Stars formed, elements forged, planets coalesced, life emerged, and now, 13.8 billion years later, on a small planet orbiting an ordinary star in an ordinary galaxy, conscious beings contemplate the journey time has taken. We look back through telescopes and see our own history written in starlight. We calculate with mathematics and reconstruct events no eye witnessed. We understand, at least partially, how we came to be. This understanding does not diminish the mystery. If anything, it deepens it. The more we learn about the universe's history, the more questions arise. What determined the initial conditions? Why these laws of physics and not others? Is our universe unique, or one of infinitely many? We may never know, but in seeking answers, in pushing the boundaries of knowledge, in asking how time began, we fulfill something essential to being human. We reach beyond ourselves towards something vast and ancient and profound. Time was born, and in time we were born, and in this moment, time contemplates its own birth. That is wonder enough for any universe. During the Dark Ages, gravity orchestrates a slow but inexorable transformation. The universe is not perfectly uniform. Those tiny fluctuations from inflation, those 1 part in 100,000 variations in density, are everywhere. And wherever there's a density enhancement, gravity amplifies it. In a region slightly denser than average, gravity is slightly stronger. This stronger gravity pulls in nearby matter, making the region even denser. As it becomes denser, its gravity becomes stronger still, pulling in more matter. This is gravitational instability, a runaway process where dense regions become denser and underdense regions become emptier. The process is slow at first. Gravity is the weakest of the fundamental forces. A density enhancement of 1 part in 100,000 creates only a tiny gravitational advantage. But time is on gravity's side. The universe expands, but it expands everywhere at the same rate. Density contrasts grow. What was 1 part in 100,000 becomes 1 part in 10,000, then 1 part in 1,000. The pattern of growth is not random. The initial density fluctuations from inflation had structure. They varied on different scales. Some fluctuations spanned millions of light years, others thousands, others mere light years. Each scale grows at its own rate, determined by the balance between gravity pulling inward and expansion pulling outward. Smaller structures collapse first. On scales of thousands of light years, density enhancements can double, triple, grow tenfold, while larger structures are just beginning to respond. The universe develops structure hierarchically, from small to large. First, small dark matter halos form. These halos merge to form larger halos. Ordinary matter falls into these halos, concentrating in their centers, preparing the stage for star formation. By about 100 million years after the Big Bang, the first substantial dark matter halos have formed. These are gravitational wells, regions where dark matter has concentrated enough that ordinary matter falling in can reach high densities and temperatures. A typical first-generation halo might contain 1 million solar masses of dark matter, spread across a few hundred light years. This doesn't sound like much. It's tiny compared to a modern galaxy like the Milky Way, which contains hundreds of billions of solar masses. But it's enough. It's enough to trap gas, to compress it, to heat it through gravitational contraction. As ordinary matter, neutral hydrogen and helium gas, falls into these dark matter halos, it accelerates. Gravitational potential energy converts to kinetic energy. The gas heats up. Atoms collide more violently. The gas would like to collapse all the way to the center of the halo, but it can't do so immediately. It has angular momentum, some small amount of rotation inherited from tidal interactions with neighboring structures. This angular momentum prevents direct collapse. Instead, the gas settles into a rotating disk or a lumpy, turbulent cloud within the dark matter halo. As it settles, it continues to heat. Atoms collide energetically. Usually, such collisions would cause the gas to heat up indefinitely, with pressure preventing further collapse. But the universe has a cooling mechanism: radiation. When atoms collide, electrons jump to higher energy states. When they fall back down, they emit photons. These photons escape into space, carrying energy away. The gas cools. As it cools, pressure drops. As pressure drops, gravity can compress the gas further. The gas collapses, heats from compression, cools by radiation, collapses further. This process continues. The cooling process in these first gas clouds is crucial, and it depends on chemistry, specifically the chemistry of primordial hydrogen and helium. This chemistry is extremely simple compared to what we're familiar with. There are no heavy elements yet, no carbon or oxygen or nitrogen, just hydrogen, helium, and trace amounts of deuterium and lithium. Neutral hydrogen atoms don't radiate efficiently at the temperatures in these early gas clouds, which are a few thousand Kelvin or less. Hydrogen atoms need to be excited to specific energy levels to emit photons, and at these temperatures, most collisions don't have enough energy. Helium is even worse. It's chemically inert and doesn't radiate at all at these temperatures. But hydrogen has a secret weapon, hydrogen molecules, H2. When two hydrogen atoms combine to form H2, the molecule can radiate in ways that atoms cannot. Molecular hydrogen has rotational and vibrational energy levels that are closely spaced. Even low-energy collisions can excite these levels. When the molecule de-excites, it emits infrared photons. These photons escape the cloud, carrying energy away, allowing the gas to cool below what atomic hydrogen alone could achieve. The gas can cool to a few hundred Kelvin, maybe as low as 200 Kelvin. This cooling is essential. The colder the gas, the lower its pressure, the more gravity can compress it, the denser it can become. But forming H2 in a universe with only hydrogen and helium is difficult. The process requires intermediate steps involving hydrogen ions and free electrons, or hydrogen atoms in excited states. It's slow and inefficient. Only a tiny fraction of hydrogen becomes molecular, maybe 1 molecule per 1,000 atoms. But this tiny fraction is enough. As gas continues to fall into the dark matter halos, as it cools and compresses, density and temperature rise in the center. The gas cloud fragments. Turbulence and instabilities create dense knots within the larger cloud. Each knot continues to collapse under its own gravity. There's a threshold that must be crossed for star formation to begin. The gas must reach a critical density and temperature where nuclear fusion can ignite. For hydrogen fusion, the process that powers stars, this requires temperatures of about 10 million Kelvin in the core. At lower temperatures, protons lack the kinetic energy to overcome their electromagnetic repulsion and fuse together. The first collapsing gas clouds are trying to reach this threshold. As they collapse, gravitational potential energy converts to heat. The center of the cloud gets hotter and denser. If the cloud can cool efficiently enough to keep collapsing, if it can avoid fragmenting into pieces too small to reach fusion temperatures, if it can gather enough mass, it will succeed. But there's a problem. These first clouds are made only of hydrogen and helium. Modern star formation relies on heavier elements, carbon, oxygen, silicon, to help cool the gas through radiation. These elements have many closely spaced energy levels and radiate efficiently. They allow gas to cool to very low temperatures and fragment into small pieces, forming stars with a wide range of masses, from less than 1/10 of a solar mass to hundreds of solar masses. The first clouds don't have these heavy elements. Their cooling is limited by molecular hydrogen, which is less efficient. This means the first clouds can't fragment as easily. They can't cool as effectively. The gas clumps that form are larger, more massive than typical modern star-forming regions. The first stars to form in the universe are unlike any stars we see today. Astronomers call them population 3 stars, following a naming convention where population 1 stars are young, metal-rich stars like the Sun, population 2 stars are old, metal-poor stars in the galactic halo and globular clusters, and population 3 stars are the hypothetical first generation with no metals at all. In astronomy, metals means any element heavier than helium. Population 3 stars are made purely of primordial hydrogen and helium, with only trace amounts of lithium. This composition profoundly affects their properties. Without heavy elements to help cool the gas, the first star-forming clouds cannot fragment into small pieces. Computer simulations suggest that the first stars are massive, perhaps 30, 100, or even 300 times the mass of the Sun. There are no small population 3 stars. The minimum mass is likely around 30 solar masses, far larger than the minimum mass of about 0.08 solar masses for modern stars. These massive stars are extraordinarily hot and luminous. A star 100 times the Sun's mass shines with perhaps 1,000,000 times the Sun's luminosity. Its surface temperature exceeds 50,000 Kelvin, compared to the Sun's 5,800 Kelvin. It burns hydrogen in its core at a prodigious rate, fusing atoms through the CNO cycle if even trace amounts of carbon, nitrogen, and oxygen are present, or through the proton-proton chain and triple alpha process. These stars are short-lived. A star's lifetime is roughly proportional to its mass divided by its luminosity. Massive stars have more fuel but burn it vastly faster. A 100 solar mass population 3 star might live only 2 or 3 million years before exhausting its core hydrogen. When the first population 3 star ignites, perhaps 100 or 200 million years after the Big Bang, the universe changes. For the first time since recombination, there is light, not the fading afterglow of the Big Bang, but new light from nuclear fusion, starlight. This first star shines in the darkness, a brilliant beacon in an otherwise dark universe. Its light travels outward at the speed of light, expanding as a sphere into the surrounding neutral hydrogen gas. The star emits primarily ultraviolet radiation, high-energy photons capable of ionizing hydrogen atoms. As this ultraviolet light encounters neutral hydrogen, it strips electrons from atoms. Each photon can ionize one hydrogen atom, creating a region of ionized gas around the star. This region is called an HII region, astronomers' notation for ionized hydrogen. The HII region expands outward from the star, growing as more photons stream out. The ionized gas behaves differently from neutral gas. As hotter, ionization heats the gas to about 10,000 Kelvin. It's more pressure supported. The added thermal energy creates pressure that resists gravitational collapse. And crucially, it's transparent to visible light, though it still absorbs and scatters ultraviolet photons. But one star, even a massive one, creates only a small ionized bubble in the vast neutral universe. The bubble might be a few light years or a few tens of light years across, depending on the star's luminosity and the density of surrounding gas. Beyond this bubble, the universe remains dark and neutral. More stars must form. The first star's light and energy influence nearby gas clouds, sometimes triggering new star formation, sometimes suppressing it. Slowly, more population 3 stars ignite in other dark matter halos scattered across the universe. Population 3 stars live fast and die young. After only a few million years, the most massive among them exhaust their core hydrogen. They begin fusing helium into carbon and oxygen, then carbon into neon and magnesium, then neon into oxygen and silicon, building heavier elements through successive fusion stages. This process accelerates as the star ages. Hydrogen fusion might last 2 million years. Helium fusion lasts a few 100,000 years. Carbon fusion lasts a few centuries. Silicon fusion, the final stage before iron, lasts only days. The star is racing toward an inevitable end. Iron is the finish line. Fusing iron requires energy input rather than releasing energy. Once an iron core forms, fusion stops. The core, now supported only by electron degeneracy pressure, can hold only a certain mass, about 1.4 solar masses, the Chandrasekhar limit. For a massive population 3 star, the core quickly exceeds this limit. When it does, catastrophic collapse begins. The core implodes in a fraction of a second, compressing from the size of Earth to the size of a city. Electrons and protons are crushed together, forming neutrons and releasing neutrinos. The collapse halts when nuclear density is reached, and the core rebounds. This rebound sends a shock wave outward through the infalling stellar envelope. The shock wave tears the star apart. The outer layers explode into space at speeds of thousands of kilometers per second. This is a supernova, specifically a core collapse supernova, one of the most energetic events in the universe. For a few weeks, this single exploding star can outshine an entire galaxy. The supernova releases as much energy in a few seconds as the Sun will emit in its entire 10 billion-year lifetime. The supernova explosion of a population 3 star is more than just spectacular light and energy. It's a cosmic forge, creating heavy elements that never existed before in the universe. During the explosion, temperatures and pressures become so extreme that nuclei can fuse into elements heavier than iron. In the normal fusion process inside a star, elements up to iron are created. But iron is the most stable nucleus. It has the highest binding energy per nucleon. Fusing iron into heavier elements requires energy input. Stars cannot do this through normal fusion. But in the extreme conditions of a supernova, neutrons are abundant. Atomic nuclei can capture these neutrons rapidly, building heavier and heavier elements through the R process, rapid neutron capture. A nucleus captures a neutron, then another, faster than it can decay. Elements like gold, platinum, uranium are created this way. Other processes create other elements. The S process, slow neutron capture, occurred in the star's late evolutionary stages. Explosive nucleosynthesis during the shock wave passage creates intermediate mass elements. Radioactive decay of unstable isotopes created in the explosion produces still more elements. When the supernova ejecta expand into the surrounding gas, they carry these newly forged elements with them. For the first time, the universe contains carbon, oxygen, nitrogen, silicon, iron, all the elements necessary for planets and life. The gas that was pure hydrogen and helium is now enriched, polluted with heavy elements. This enriched gas will eventually be incorporated into new stars. Those second-generation stars will have different properties than population 3 stars because they contain metals. They can cool more efficiently. They can form planets. They are stars like our Sun, stars capable of hosting life. The death of the first population 3 stars marks a fundamental transition in cosmic history. Before these explosions, the universe contained only primordial elements, hydrogen, helium, and traces of lithium created in Big Bang nucleosynthesis. After these explosions, heavy elements exist for the first time. The supernova ejecta expand outward in a rapidly moving shell, plowing into the surrounding neutral hydrogen gas. This creates a shock wave, heating and compressing the gas. The shock can trigger new star formation in dense regions, or it can disperse gas clouds, preventing star formation. The effect depends on the density and structure of the surrounding medium. As the ejecta expand, they mix with the primordial gas. Turbulence and instabilities cause the metal-enriched material to blend with pure hydrogen and helium. The mixing is not perfect. Some regions become more enriched than others, but gradually, the heavy elements disperse through larger and larger volumes. The first generation of stars may have been massive and short-lived, but their impact is permanent. They have fundamentally changed the chemical composition of the universe. The metallicity, the fraction of elements heavier than helium, has increased from essentially 0 to perhaps 1/millionth or 100,000th of the Sun's metallicity. This seems tiny, but it's enough to affect how the next generation of stars forms. Gas clouds that incorporate even small amounts of heavy elements can cool more efficiently. Carbon and oxygen atoms radiate energy through emission lines. Silicon and iron provide additional cooling pathways. This enhanced cooling allows gas to fragment into smaller clumps, enabling the formation of smaller stars. The second generation of stars will have a wider range of masses, more like the stars we observe today. As enriched gas settles into dark matter halos, the second generation of stars begins to form. These are not pure population 3 stars. They contain small amounts of heavy elements from the first supernovae. Astronomers call them population 2.5 stars, or very metal-poor population 2 stars. These stars span a wider mass range than population 3 stars. Some are still quite massive, 30, 50, 100 solar masses, but others are smaller. For the first time, stars with masses similar to the Sun can form. Some may even be smaller, though the minimum mass is still uncertain and depends on the exact metallicity. Lower mass stars live far longer than massive stars. A star with the Sun's mass lives about 10 billion years. A star with half the Sun's mass lives over 100 billion years, longer than the current age of the universe. If any of these low-mass, metal-poor stars formed in the very early universe, they should still exist today, ancient fossils from cosmic dawn. Astronomers search for such stars in the Milky Way's halo. They found extremely metal-poor stars, stars with metallicities 100,000th or even 1/1,000,000th of the Sun's. These stars likely formed early in cosmic history, perhaps within the first billion years. Their chemical compositions tell us about the supernovae that enriched the gas from which they formed. Interestingly, we've never found a star with exactly 0 metallicity, a true population 3 star. This makes sense. Massive population 3 stars are short-lived, and they all died billions of years ago. Only if a small population 3 star could form would it survive to today. But our models suggest population 3 stars were always massive. The first low-mass, long-lived stars were probably already slightly metal-enriched. By 200 or 300 million years after the Big Bang, star formation is accelerating. It's no longer one star here, another there, isolated beacons in darkness. Dark matter halos are growing through mergers, creating larger gravitational wells. More gas is accumulating. Multiple generations of stars are forming in the same regions. In a typical early halo, the process unfolds like this. A first-generation population 3 star forms and lives for a few million years. It explodes as a supernova, enriching nearby gas with heavy elements. This enriched gas, along with fresh primordial gas from the cosmic web, continues falling into the dark matter halo. After some tens of millions of years, enough gas has accumulated for a second episode of star formation. This time, the stars are slightly metal-enriched. Some are massive and will explode quickly. Others are lower mass and will live for billions of years. The massive stars explode, further enriching the gas. The cycle continues. Each generation enriches the gas more. Each generation produces a wider range of stellar masses. Gradually, small clusters of stars form, dozens or hundreds of stars in a volume a few light-years across. These are not yet galaxies, but they're proto-galactic building blocks. The light from these star clusters begins to have a cumulative effect. Each cluster creates an ionized bubble in the neutral hydrogen around it. Initially, these bubbles are isolated, separated by vast dark regions. But as more clusters form, as more stars ignite, the bubbles grow and begin to overlap. The neutral hydrogen between halos starts to ionize. The universe is entering the epoch of reionization. The period when the first stars formed, roughly 100 to 400 million years after the Big Bang, is called cosmic dawn. It's the end of the dark ages, the beginning of a luminous universe. But observing cosmic dawn directly is extraordinarily difficult. The light from these first stars is redshifted by cosmic expansion. A photon emitted in the ultraviolet by a population 3 star at redshift 20 or 30 corresponding to 100 or 200 million years after the Big Bang, arrives at Earth today in the infrared with its wavelength stretched by a factor of 20 or 30. Moreover, these first stars are individually faint and distant. Even the most powerful telescopes struggle to detect individual population 3 stars. The James Webb Space Telescope, launched in 2021, is designed partly to search for light from cosmic dawn. It observes in the infrared, where the redshifted light from early stars appears. What astronomers hope to find are not individual stars but galaxies in formation, collections of stars and gas in the process of assembling. Even a small protogalaxy with millions of stars would be detectable if we look deep enough. The light from these early galaxies tells us when star formation began, how rapidly it proceeded, and what properties the first stellar populations had. Another way to study cosmic dawn is through the 21-centimeter line of neutral hydrogen. Hydrogen atoms emit radio waves at a wavelength of 21 centimeters due to a quantum transition called hyperfine splitting. In the early universe, neutral hydrogen filled space. This hydrogen absorbed photons from the cosmic microwave background at the 21-centimeter wavelength, creating an absorption signal. When the first stars formed, their ultraviolet light altered the quantum states of nearby hydrogen atoms, changing the 21-centimeter absorption. The 21-centimeter signal from cosmic dawn carries information encoded in subtle variations across the sky. Different regions began forming stars at different times, depending on the local dark matter distribution and gas density. Where stars formed earlier, the 21-centimeter signal changed earlier. Before any stars formed, neutral hydrogen everywhere absorbed cosmic microwave background photons at 21 centimeters, creating a uniform absorption signal. When the first stars ignited, they emitted ultraviolet light called Lyman alpha radiation. This radiation, when absorbed by hydrogen atoms, excited electrons to higher energy levels. These excited atoms changed how they interacted with 21-centimeter photons. In some conditions, this enhanced the absorption. In others, it reduced it. The signal became patchy, varying from place to place depending on proximity to stars and the intensity of their radiation. Later, as more stars formed and their ultraviolet light intensified, they began ionizing hydrogen. Ionized hydrogen doesn't produce a 21-centimeter signal at all. The signal only comes from neutral atoms. So regions around star clusters became invisible in 21-centimeter observations, appearing as holes in the otherwise absorbing neutral gas. Detecting this signal from Earth is challenging. The signal is faint, redshifted to radio wavelengths between about 50 and 200 megahertz. Earth's atmosphere and human-generated radio interference contaminate these frequencies. Specialized radio telescopes in remote locations like the Australian outback or the South African desert are being built to detect it. If successful, 21-centimeter observations would provide a three-dimensional map of star formation during cosmic dawn. We could see how the first stars lit up the universe, region by region, transforming it from neutral to ionized. As stellar populations multiply and evolve, as star clusters merge and grow, the cumulative effect of all the starlight becomes significant. By about 400 million years after the Big Bang, enough stars have formed that their collective ultraviolet radiation begins to reionize the universe. Remember, the universe was ionized in its earliest moments, hot plasma where electrons and nuclei were separate. Then, at recombination 380,000 years after the Big Bang, it became neutral as electrons bound to nuclei. Now, stellar ultraviolet radiation is stripping electrons from atoms again, ionizing hydrogen for the second time in cosmic history. This reionization doesn't happen everywhere simultaneously. It begins in the densest regions, where dark matter halos are largest and star formation is most vigorous. Each cluster of stars creates an ionized bubble. These bubbles grow as more ultraviolet photons stream out from stars. Initially, the bubbles are small and isolated, separated by vast neutral regions. The universe is like Swiss cheese, ionized holes in a neutral medium. But the bubbles expand. New stars form, creating new bubbles. The bubbles merge when they meet, creating larger ionized regions. The process is complex and inhomogeneous. Dense filaments of the cosmic web, where gas concentrations are high, ionize first. Voids, where gas is sparse, remain neutral longer. The morphology of reionization reflects the cosmic web structure, filamentary and interconnected. Computer simulations show reionization as a percolation process. Individual bubbles grow and merge until suddenly, at some critical point, they connect across the entire universe. A network of ionized channels forms, and the remaining neutral regions become isolated pockets rather than the dominant phase. Reionization is not a single event but an extended epoch, lasting several hundred million years. It begins around 400 million years after the Big Bang, when the first substantial ionized bubbles form. It completes around 1 billion years after the Big Bang, when the last neutral regions are ionized. During this epoch, the universe transforms from mostly neutral to mostly ionized. The fraction of neutral hydrogen drops from nearly 100% to less than 0.01%. This transformation is driven primarily by stars, though other sources may contribute. Massive stars emit copious ultraviolet radiation. When these stars are numerous enough, when their combined ultraviolet output exceeds the rate at which hydrogen recombines, the neutral gas cannot maintain itself. Ionization wins. The universe tips from neutral to ionized. But there's a complication. Not all the ultraviolet photons from stars escape into the intergalactic medium. Some are absorbed by gas and dust within the galaxies where the stars reside. The escape fraction, the percentage of ultraviolet photons that escape their host galaxy, is crucial for reionization. If the escape fraction is high, say 50%, then relatively few stars are needed to reionize the universe. If it's low, say 5%, then many more stars are required. Observations and simulations suggest escape fractions of 10 to 20% for typical early galaxies, though this varies widely depending on galaxy mass, star formation rate, and gas content. Another possible contributor to reionization is quasars, supermassive black holes accreting gas and emitting enormous amounts of radiation. Quasars are observed at high redshifts, and their ultraviolet output is substantial. However, quasars seem too rare in the early universe to dominate reionization. Stars are likely the primary driver. As reionization progresses, neutral hydrogen retreats to its final strongholds, the densest, most shielded regions where ultraviolet radiation cannot easily penetrate. These are typically the cores of dark matter halos that are actively forming stars, or dense filaments of the cosmic web. Paradoxically, the densest star-forming regions can remain neutral longest. They produce ultraviolet radiation, but they also contain so much gas that the radiation is absorbed locally before escaping. The gas shields itself from the external radiation field through self-shielding. In these dense regions, star formation continues even as reionization proceeds around them. They are like islands of neutral gas in an ionized ocean. Eventually, however, even these regions succumb. Either their internal radiation ionizes them from within, or the external radiation field becomes so intense that it overwhelms the shielding. By about 1 billion years after the Big Bang, observations suggest the universe is more than 99% ionized. The remaining neutral hydrogen exists in dense pockets within galaxies, in the cores of the highest redshift systems that are just beginning to form, or in isolated clouds in the intergalactic medium. Some of this neutral hydrogen persists to the present day. The interstellar medium of galaxies contains neutral regions. Clouds in intergalactic space occasionally show neutral hydrogen absorption in quasar spectra. But the universe as a whole has been ionized for over 12 billion years. Reionization marks the end of one era and the beginning of another. The dark ages are over. The first stars have lived and died. The first galaxies are assembling. The universe has entered the epoch of galaxy formation, the era that leads eventually to the cosmos we observe today. While reionization transforms the intergalactic medium, within dark matter halos, galaxies are taking shape. These early galaxies are nothing like the majestic spiral and elliptical galaxies we see in the nearby universe. They are small, chaotic, irregular collections of stars and gas. A typical protogalaxy at redshift 10, about 500 million years after the Big Bang, might contain a few million to a few hundred million stars. Its total mass, including dark matter, might be 1 billion solar masses or less. It spans a few thousand light-years, far smaller than the 100,000 light-year diameter of the Milky Way. Star formation in these protogalaxies is intense but sporadic. Gas falls in from the cosmic web, accumulating until it reaches densities high enough to form stars. A burst of star formation occurs, creating thousands of massive stars. These stars live briefly and explode as supernovae. The supernova energy heats the gas, sometimes expelling it from the galaxy entirely. After the outburst, star formation may pause for millions of years while gas cools and reaccumulates. Then another burst occurs. This cycle of star formation, feedback, quiescence, and renewed star formation characterizes early galaxy evolution. The feedback from supernovae is crucial. Without it, all the gas would quickly turn into stars, and galaxies would be more massive than observed. Supernova energy regulates star formation, preventing it from being too efficient. The interplay between gas inflow from the cosmic web, star formation, and supernova-driven outflows determines the properties of these early galaxies. Some protogalaxies grow by merging with neighbors. Dark matter halos collide and merge, bringing their stellar populations together. These mergers can trigger intense star formation. Galaxy formation is a hierarchical process. Small structures form first, then merge to create larger structures. This hierarchy is driven by dark matter, which dominates the gravitational dynamics. In the early universe, dark matter fluctuations on small scales collapse first. Halos with masses of 1 million solar masses form by 100 million years after the Big Bang. These halos merge to form larger halos. 2 million solar mass halos merge to create a 2 million solar mass halo. Multiple small halos merge to create 10 million solar mass halos, then 100 million solar mass halos. Each time halos merge, their stellar populations merge too. If two protogalaxies, each containing 10 million stars, merge, the result is a galaxy with 20 million stars. The stars from both progenitors mix together, creating a larger, more massive system. This process continues over cosmic time. The largest galaxies in the present-day universe, giant ellipticals in galaxy clusters, formed through hundreds or thousands of mergers over billions of years. They are the accumulated product of hierarchical assembly. But mergers are not the only growth mechanism. Galaxies also grow by accreting gas from the cosmic web. Gas flows along dark matter filaments, channeling toward the densest nodes where galaxies reside. This cold mode accretion brings fresh fuel for star formation. In the early universe, cold mode accretion dominates. Gas streams into galaxies along narrow filaments, maintaining relatively low temperatures. This gas can form stars immediately. Later in cosmic history, as halos become more massive, gas accreting onto them shocks to high temperatures, creating hot halos. This hot mode accretion is less efficient at forming stars. The balance between mergers and gas accretion, between cold and hot modes, shapes galaxy evolution. As the first galaxies assemble, something mysterious begins to happen in their centers. Supermassive black holes start to form. These are not the stellar mass black holes created when massive stars collapse. Those contain a few to a few hundred solar masses. Supermassive black holes contain millions or billions of solar masses. How these giants form so early in cosmic history remains one of astronomy's deepest puzzles. By 700 million years after the Big Bang, astronomers have observed quasars, luminous objects powered by black holes containing a billion solar masses or more. How did black holes grow so massive so quickly? There are several proposed pathways. The most straightforward is sequential growth. A massive population 3-star collapses to form a black hole with perhaps 100 solar masses. This black hole accretes gas from its surroundings, growing gradually. As it accretes, it emits radiation that can prevent further accretion, limiting growth rate. If a black hole accretes at the maximum possible rate, the Eddington limit where radiation pressure balances gravitational infall, it can double its mass every few tens of millions of years. Starting from 100 solar masses, growing at the Eddington limit continuously, a black hole could reach 1 billion solar masses in about 700 million years. But there's a problem. Achieving continuous Eddington-limited accretion is difficult. The radiation from the accreting black hole heats and ionizes surrounding gas, often shutting down accretion. Growth tends to be episodic, not continuous. This makes it challenging to grow billion solar mass black holes so early. Alternative formation mechanisms have been proposed. Perhaps some black holes formed directly from the collapse of massive gas clouds, creating seeds of thousands or tens of thousands of solar masses, giving them a head start. One promising formation channel for supermassive black holes is direct collapse. Instead of forming a star first and then a black hole from the star's core, an entire gas cloud collapses directly into a black hole, creating a massive seed. For direct collapse to work, the gas cloud must avoid fragmenting into stars. This requires suppressing normal star formation cooling mechanisms. If molecular hydrogen can form and cool the gas, the cloud fragments into stars. But if molecular hydrogen is destroyed or prevented from forming, the gas remains hot and doesn't fragment. How can molecular hydrogen be suppressed? One way is through a strong ultraviolet radiation background. If a nearby galaxy or star cluster bathes the gas cloud in ultraviolet light, this radiation can dissociate molecular hydrogen molecules, breaking them apart. Without H2 cooling, the gas cannot cool below about 8,000 Kelvin. At this temperature, the gas can collapse under gravity, but it remains too hot to fragment. Instead of forming many small stars, the entire cloud, containing perhaps 100,000 or 1 million solar masses, collapses into a single object. This object is too massive to be supported by any known mechanism, cannot become a star, collapses all the way to a black hole. This direct collapse creates what astronomers call a supermassive star or quasi-star, a brief, unstable configuration where a black hole forms at the center while the outer envelope is still collapsing. The black hole quickly accretes the surrounding material, growing rapidly to tens of thousands of solar masses. Starting from such a massive seed makes it much easier to reach billion solar mass black holes by 700 million years after the Big Bang. The black hole needs to grow by only a factor of 100 or so, achievable even with episodic accretion. Once supermassive black holes form, some begin accreting gas at prodigious rates. Gas spirals inward, forming an accretion disk around the black hole. Friction in the disk heats the gas to millions of degrees. This hot gas radiates enormous amounts of energy across the electromagnetic spectrum: X-rays, ultraviolet, visible light, infrared, radio waves. The luminosity can be staggering. A supermassive black hole accreting at the Eddington limit can outshine an entire galaxy. A billion solar mass black hole can emit as much light as 1 trillion suns. These ultraluminous objects are called quasars, short for quasi-stellar radio sources, named when they were first discovered in the 1960s as point-like radio sources. The first quasars appear surprisingly early. By about 700 million years after the Big Bang, multiple quasars have been discovered. These early quasars are among the most distant objects we can observe. Their light has traveled for over 13 billion years to reach us, showing us the universe as it was in its infancy. These quasars tell us that supermassive black holes and vigorous accretion were already present when the universe was only about 5% of its current age. Galaxy formation, black hole formation, and reionization were happening simultaneously, influencing each other in complex ways. Quasars contribute to reionization by emitting copious ultraviolet radiation. A single bright quasar can ionize a region of space millions of light-years across. However, quasars are rare. There are far more normal star-forming galaxies than quasars. So while quasars contribute to reionization, stars in ordinary galaxies likely do most of the work. Quasars also affect their host galaxies through feedback. The radiation and jets from accreting black holes can heat or expel gas. The relationship between supermassive black holes and their host galaxies is symbiotic and complex. Black holes grow by accreting gas from their galaxies. But as they accrete, they release energy that affects the gas, regulating or preventing further star formation. This is called AGN feedback, active galactic nucleus feedback, where AGN refers to the accreting black hole and its surrounding luminous region. There are two main types: radiative feedback and mechanical feedback. Radiative feedback occurs when photons from the accretion disk interact with gas in the galaxy. Ultraviolet photons ionize and heat the gas. The heated gas gains pressure support and may expand or be driven out in winds. If enough gas is expelled, star formation shuts down because there's no fuel left. Mechanical feedback occurs through jets and outflows. Many accreting black holes launch powerful jets of plasma perpendicular to the accretion disk. These jets, moving at nearly the speed of light, plow into the surrounding gas, creating shock waves. The shock waves heat the gas, sometimes to millions of degrees, preventing it from cooling and forming stars. Outflows, winds of gas driven from the accretion disk, also carry energy into the surrounding medium. These winds can reach speeds of thousands of kilometers per second, sufficient to unbind gas from the galaxy's gravitational potential. The net effect is that black hole accretion can regulate star formation. When a galaxy is forming stars rapidly and feeding its central black hole, the black hole grows until its feedback becomes strong enough to shut down star formation. This creates a self-regulating cycle that may explain observed correlations between black hole mass and galaxy properties. In the early universe, AGN feedback is still establishing these relationships. While individual galaxies evolve through star formation, mergers, and black hole growth, the large-scale structure of the universe is also developing. The cosmic web, the network of filaments, nodes, and voids that organizes matter on the largest scales, becomes more pronounced as time advances. At recombination, density fluctuations were tiny 1 part in 100,000. By cosmic dawn, these fluctuations have grown under gravity to density contrasts of order unity. Some regions twice as dense as average, others half as dense. By 500 million to 1 billion years after the Big Bang, the cosmic web is clearly defined. Dark matter dominates the gravitational dynamics. Dark matter halos collapse and merge, creating larger halos. These halos are not distributed randomly. They form along filaments, elongated structures tens of millions of light-years long. Where filaments intersect, massive halos cluster together, creating nodes or knots in the web. Between filaments lie voids, vast underdense regions where matter has drained away into surrounding structures. Voids can be tens or hundreds of millions of light-years across, containing few galaxies or dark matter halos. Ordinary matter follows dark matter's gravitational lead. Gas flows along filaments toward nodes. This flow is not smooth but turbulent and clumpy. Gas shocks when streams collide, heating to temperatures of hundreds of thousands or millions of degrees. Some gas cools and condenses, forming stars. Other gas remains hot, filling the space between galaxies. Observations of distant galaxies reveal this structure. Galaxies are not scattered randomly across the sky. They cluster along lines and at intersections, outlining the cosmic web. By mapping galaxy positions at different distances, and thus different times, we trace the web's evolution. The filaments of the cosmic web are not static. They are conduits of matter flowing toward the densest regions. Gas and dark matter stream along filaments at hundreds of kilometers per second, channeling toward galaxy clusters forming at the nodes. These flows are called cold flows or cold mode accretion. The gas remains relatively cool, tens of thousands of degrees rather than millions, because it flows so rapidly that it doesn't have time to shock heat. The gas follows the narrowest, densest channels of the filament, threading through lower density regions without thermalizing. When cold flows reach a galaxy, they deliver fresh fuel for star formation. This fuel is pristine or only slightly enriched with heavy elements, unlike the gas already processed through stars in the galaxy. The continuous delivery of fresh gas sustains star formation over hundreds of millions or billions of years. In the early universe, cold flows dominate galaxy growth. Most gas reaches galaxies this way rather than through hot accretion or mergers. The narrow, fast flows can penetrate deep into dark matter halos, reaching the central galaxy without being shock-heated. Later, as halos become more massive, cold flows become less effective. In very massive halos, those exceeding about 1 trillion solar masses, infalling gas shocks to high temperatures, creating hot halos. Gas in these hot halos must cool radiatively before it can form stars, which takes longer and is less efficient. The transition from cold to hot accretion occurs around redshift 2 or 3, about 2 to 3 billion years after the Big Bang. Before this transition, cold flows dominate. After, hot halos regulate star formation in massive systems. This transition shapes the evolution of galaxies and the decline of cosmic star formation rate. At the nodes of the cosmic web, where multiple filaments intersect, the most massive structures in the universe begin to form, galaxy clusters. These are gravitationally bound systems containing hundreds or thousands of galaxies, along with vast amounts of hot gas and dark matter. The first protoclusters appear around 500 million to 1 billion years after the Big Bang. These are not yet the rich, massive clusters we observe in the nearby universe, but their progenitors, overdense regions containing dozens of young galaxies in a volume a few million light-years across. In these overdense regions, galaxy mergers are frequent. Galaxies are packed closely together, and their random motions bring them into collision. When galaxies merge, their stars intermix, their gas clouds collide and trigger star formation, and their central black holes may eventually merge. The hot gas between galaxies in a cluster, the intracluster medium, begins to accumulate. This gas is heated by gravitational compression as the cluster assembles, and by energy input from supernovae and active galactic nuclei in member galaxies. Temperatures reach tens of millions of degrees, hot enough to emit X-rays. By 1 billion years after the Big Bang, the most massive protoclusters contain several hundred billion solar masses in dark matter, tens of billions in stars and gas, and dozens of distinct galaxies. They are well on their way to becoming the galaxy clusters we observe at later times. These clusters are special environments. Star formation rates are high because of frequent mergers and abundant gas. But clusters also begin showing signs of quenching, shutting down star formation in some member galaxies, due to processes like ram pressure stripping and strangulation. As galaxies fall into overdense regions and clusters, they encounter environments very different from the cosmic web filaments where they formed. These new environments affect their evolution, often shutting down star formation. One key process is ram pressure stripping. When a galaxy moves through the hot intracluster medium, it experiences a headwind, like a car moving through air. This ram pressure can strip gas from the galaxy, removing the fuel for future star formation. The effect is strongest for lower mass galaxies and for gas in the outer regions. Stripped gas forms tails behind galaxies, sometimes visible in radio or X-ray observations as elongated features millions of light-years long. The gas can shock heat, trigger star formation briefly in the tail, or simply mix with the intracluster medium. Another process is strangulation or starvation. When a galaxy falls into a cluster, the hot halo of gas that normally surrounds it can be stripped away by tidal forces and ram pressure. Without this reservoir, the galaxy cannot replenish gas lost to star formation and stellar winds. Star formation continues for a while, consuming remaining gas, but eventually stops when the fuel runs out. Tidal interactions with the cluster gravitational potential or with nearby galaxies can also affect evolution. Tidal forces can trigger star formation by compressing gas. They can strip stars from the outer regions of galaxies, creating intracluster stellar populations. In extreme cases, galaxies can be tidally disrupted entirely. The net result is that cluster environments tend to host older, redder, more quiescent galaxies compared to field environments. By 1 billion years after the Big Bang, this environmental dependence is beginning to emerge, foreshadowing the strong correlations between galaxy properties and environments seen in the nearby universe. As stars live and die, as supernovae explode, as galaxies evolve and interact, the heavy elements created in stellar nucleosynthesis spread through space. By 1 billion years after the Big Bang, the universe is significantly enriched compared to the primordial composition. The average metallicity of the universe has increased from essentially 0 to perhaps 1% or a few percent of the Sun's metallicity. This average conceals enormous variation. Gas that has been cycled through stars multiple times, in the central regions of actively star-forming galaxies, may have metallicities approaching or exceeding the Sun's. Gas in voids, far from any star formation, remains nearly primordial. The intergalactic medium, the gas between galaxies, also becomes enriched. Supernovae don't just enrich gas within their host galaxies. They create fast-moving ejecta that can escape the galaxy entirely, carrying heavy elements into intergalactic space. This process is called galactic winds or supernova-driven outflows. When multiple supernovae explode in a short time in a small region, their combined energy creates a superbubble, an expanding cavity of hot gas. If the galaxy is not too massive, if the superbubble breaks through the galaxy's disk or halo, the hot gas vents into intergalactic space as a galactic wind. These winds carry metals into the circumgalactic medium, the region around galaxies, and even into true intergalactic space. Once in intergalactic space, metals mix with the pristine gas in filaments. Future generations of stars will form from this enriched material. We can detect metals in intergalactic space through absorption lines in quasar spectra. When light from a distant quasar passes through intervening gas clouds, specific wavelengths are absorbed by elements like carbon, oxygen, and silicon. By 1 billion years after the Big Bang, the universe has been utterly transformed from the dark, neutral, uniform state that existed after recombination. Let us take a moment to reflect on the journey time has taken. At 380,000 years at recombination, the universe was a featureless, cooling plasma. Density varied by only 1 part in 100,000. No structures existed larger than the horizon size. The universe glowed uniformly with thermal radiation, about to transition from ionized to neutral. Then came the Dark Ages. For hundreds of millions of years, the universe was dark, neutral, and quiet. But beneath the surface, gravity was working. Dark matter clumped. Gas flowed along dark matter filaments. Tiny density fluctuations grew, slowly at first, then accelerating. Cosmic dawn arrived between 100 and 400 million years after the Big Bang. The first stars ignited, fusing hydrogen into helium and heavier elements. These stars were massive, luminous, and short-lived. They lived for only a few million years before exploding as supernovae, enriching the universe with the first heavy elements. The second generation of stars formed from slightly enriched gas. These stars had a wider mass range. Some lived long enough to survive until today. Star formation accelerated. Small proto-galaxies assembled from merging dark matter halos and accreting gas. Reionization began around 400 million years and completed around 1 billion years after the Big Bang. The neutral hydrogen that filled space was ionized by ultraviolet radiation from stars and quasars. The universe transitioned from opaque to transparent, from neutral to ionized, for the second time in its history. Supermassive black holes formed in galaxy centers and began accreting, powering the first quasars. As we move forward from 1 billion years after the Big Bang, the universe enters what astronomers call the cosmic noon, the peak era of star formation. This occurs roughly between 1 and 3 billion years after the Big Bang, corresponding to redshifts between 1 and 3. During this epoch, star formation in the universe reaches its maximum rate. Galaxies are forming stars more rapidly than at any other time in cosmic history. The cosmic star formation rate, the total mass of stars formed per year in a given volume, is about 10 times higher than today. Why does star formation peak during this era? Several factors combine. Gas is still abundant. Galaxies haven't yet consumed or expelled most of their fuel. Cold flows are still efficient at delivering fresh gas from the cosmic web. Galaxies are actively merging, and mergers trigger intense star formation. The universe is dense enough that galaxies interact frequently, but not so dense that feedback processes have shut down star formation in massive systems. In individual galaxies, star formation rates can reach hundreds of solar masses per year, compared to about 1 solar mass per year in the Milky Way today. These intensely star-forming galaxies appear as bright, compact objects in deep surveys. Some are so dusty that their visible light is absorbed and re-emitted in the infrared, making them invisible in optical observations but brilliant in infrared. The stars formed during cosmic noon constitute a large fraction of all stars that exist today. Most of the stellar mass in the universe formed during this relatively brief period. The Sun itself, which formed about 4.6 billion years ago, is a latecomer. It formed well after the peak of cosmic star formation. As galaxies mature beyond the first billion years, many begin to develop recognizable structures. The chaotic, irregular protogalaxies of cosmic dawn evolve into more organized systems. Disk galaxies, galaxies with rotating disks of stars and gas, become increasingly common. Disk formation requires angular momentum. When gas falls into a dark matter halo, it carries angular momentum from tidal torques, gravitational interactions with surrounding matter. As the gas settles toward the halo center, conservation of angular momentum prevents it from falling straight in. Instead, it forms a rotating disk perpendicular to the angular momentum vector. In the disk, gas orbits the galactic center. The inner regions orbit faster than the outer regions, following Kepler's laws modified by the dark matter distribution. Gas clouds within the disk collide, lose energy, and settle into the disk plane, creating a thin structure. Stars form from dense gas clouds in the disk. Young, hot stars trace spiral arms, density waves that propagate through the disk, compressing gas and triggering star formation. These spiral galaxies, like our Milky Way, become prominent by a few billion years after the Big Bang. Not all galaxies form disks. Some undergo major mergers, collisions with galaxies of similar mass, that destroy disk structures through violent gravitational interactions. These merger remnants often become elliptical galaxies, spheroidal systems with little organized rotation and little ongoing star formation. By 2 billion years after the Big Bang, the galaxy population includes a mix of disk galaxies, ellipticals, and irregular systems. The morphology depends on each galaxy's merger history, gas content, and environment. Galaxies in dense clusters are more likely to be elliptical due to frequent mergers and interactions. By 3 billion years after the Big Bang, the universe has undergone significant chemical enrichment. The metallicity of typical star-forming galaxies has reached perhaps 20 to 50% of the Sun's metallicity, up from nearly zero at cosmic dawn. This enrichment has profound consequences. With more heavy elements available, planets can form more easily. Rocky planets require silicon, iron, magnesium, elements created in stars and dispersed by supernovae. Gas giant planets need solid cores to form before accreting hydrogen and helium. Without heavy elements, planetary systems like our solar system cannot exist. The first potentially habitable planets likely form around this time. Stars with sufficient metallicity to form rocky planets in habitable zones, regions where liquid water can exist on planetary surfaces, become common. The building blocks of life as we know it, carbon, nitrogen, oxygen, phosphorus, sulfur, are available in the interstellar medium. However, the early universe poses challenges for life. The rate of supernovae and gamma-ray bursts is much higher than today, creating a hazardous radiation environment. Galaxies are smaller and denser, with stars packed more closely, increasing the likelihood of nearby supernovae sterilizing planetary systems. The heavy element abundances also affect stellar evolution. Stars with higher metallicity have different structures, lifetimes, and evolutionary paths than metal-poor stars. They lose more mass through stellar winds. They produce different patterns of nucleosynthesis. The chemical composition of gas from which stars form influences every aspect of stellar populations. By tracking metallicity evolution through cosmic time, astronomers trace the history of star formation and element production. The metals we detect tell us how many generations of stars have lived and died, how efficiently galaxies have converted gas into stars. Between 3 and 7 billion years after the Big Bang, the universe undergoes a gradual transition from the vigorous, rapidly evolving early universe to the more sedate, slowly evolving later universe. Star formation rates begin to decline. Merger rates decrease. Large-scale structure continues to grow but at a decelerating pace. Several processes contribute to this cosmic slowdown. Gas reservoirs in galaxies are depleted by star formation and expelled by supernova-driven winds and AGN feedback. The cosmic web has largely assembled. Filaments are established, clusters have formed, voids have expanded. Cold flows become less efficient as halos become more massive and gas shocks to high temperatures. The decline in star formation is not uniform. Massive galaxies in dense environments shut down first, transitioning to quiescent, red and dead states where little new star formation occurs. Lower mass galaxies in less dense environments continue forming stars for billions of years longer. This mass-dependent quenching creates the bimodality observed in galaxy populations. A red sequence of quiescent, elliptical, or early-type galaxies with old stellar populations, and a blue cloud of star-forming, disk-dominated galaxies with young stellar populations. The red sequence builds up over time as galaxies exhaust their gas and cease forming stars. Dark energy begins to dominate cosmic dynamics around 7 billion years after the Big Bang. For the first 7 billion years, the universe's expansion was decelerating due to the gravitational pull of matter. Dark energy, a mysterious form of energy with negative pressure, counteracts this deceleration and eventually causes the expansion to accelerate. This acceleration has profound implications for the future. Structures that have already formed continue to evolve, but the formation of new large-scale structures ceases. About 9 billion years after the Big Bang, roughly 4.6 billion years ago, a particular star forms in a particular galaxy. This star is the Sun. Its formation is unremarkable in cosmic terms, but it is the event that leads eventually to life on Earth and to conscious beings asking about the universe's origins. The Sun forms in a molecular cloud in the Milky Way's disk. This cloud has been enriched by previous generations of stars. Its metallicity is about twice that of the universe's average at that time, roughly 2% by mass in elements heavier than helium. This enrichment is crucial. It provides the raw materials for planets. As the proto-sun collapses, a disk of gas and dust forms around it. In this protoplanetary disk, small dust grains stick together through electrostatic forces. These grains accumulate into pebbles, then boulders, then planetesimals, objects kilometers across. Planetesimals collide and merge, growing into planetary embryos. In the inner solar system, rocky planets form: Mercury, Venus, Earth, Mars. In the outer solar system, beyond the frost line where water ice is stable, giant planets form: Jupiter, Saturn, Uranus, Neptune. These giants form by accreting massive atmospheres of hydrogen and helium onto solid cores. The Earth forms through violent collisions. A Mars-sized body, sometimes called Theia, crashes into the proto-Earth, ejecting debris that coalesces into the moon. The impact melts Earth's surface, creating a magma ocean. Gradually, the planet cools. Water, delivered by comets and asteroids, accumulates in oceans. An atmosphere forms from volcanic outgassing. By 4 billion years ago, Earth has cooled enough for liquid water to exist on its surface. The stage is set for life to emerge. We arrive at 13.8 billion years after the Big Bang, the present day. The universe has evolved from a hot, dense, uniform state to a vast, complex structure filled with galaxies, stars, planets, and at least one world bearing intelligent life. The cosmic microwave background, once visible light at recombination, has been stretched by expansion into microwaves with a temperature of 2.7 Kelvin. This faint glow fills the sky uniformly, carrying information about the universe at 380,000 years old. Galaxies span a wide range of masses, morphologies, and star formation rates. Giant ellipticals in cluster centers contain trillions of stars but form few new ones. Spiral galaxies like the Milky Way continue forming stars at modest rates. Dwarf galaxies orbit larger galaxies as satellites, some still forming stars, others quenched by tidal effects. Supermassive black holes reside in the centers of most large galaxies, their masses correlated with their host galaxy's properties. Some accrete actively, powering quasars and active galactic nuclei. Most are quiescent, accreting slowly or not at all. The large-scale structure is fully developed. The cosmic web of filaments, clusters, and voids extends across billions of light-years. Dark matter dominates the mass distribution. Dark energy dominates the expansion dynamics, driving accelerated expansion. Star formation continues, but at a fraction of the peak rate during cosmic noon. Most stars that will ever form have already formed. The universe is in a slow decline toward a dimmer, colder future. On Earth, life has evolved from simple single-celled organisms 4 billion years ago to complex multicellular life, and eventually to humans. We look out at the universe with telescopes, gathering ancient light, reconstructing the history we have traced. From our vantage point in the present, we can observe the universe's history directly. Light travels at a finite speed, about 300,000 kilometers per second. When we observe distant objects, we see them not as they are now, but as they were when their light left them. Look at the moon and you see it as it was 1.3 seconds ago. Look at the sun and you see it as it was 8 minutes ago. Look at the nearest star, Proxima Centauri, and you see it as it was 4 years ago. The farther we look, the farther back in time we see. Telescopes are time machines. The Hubble Space Telescope and James Webb Space Telescope observe galaxies billions of light-years away, seeing them as they were billions of years ago. We can observe galaxies forming stars during cosmic noon. We can detect the light from reionization. We can see the cosmic microwave background from recombination. This ability to look back in time is one of cosmology's greatest advantages. Unlike geologists studying Earth's ancient history through fragmentary rocks, or biologists inferring evolution from fossils, astronomers can directly observe the past. We don't have to infer what early galaxies looked like. We can point telescopes at them and see. The most distant galaxies observed are seen as they were only a few 100 million years after the Big Bang, during or shortly after cosmic dawn. Their light has traveled for over 13 billion years, stretched from ultraviolet into infrared by cosmic expansion. But we cannot see beyond recombination. The opaque plasma before that time blocks our view. The cosmic microwave background is the ultimate barrier to optical and infrared observation. Though photons cannot penetrate beyond recombination, other messengers can. Neutrinos and gravitational waves, created in the very early universe, can reach us from earlier times. The cosmic neutrino background was created when neutrinos decoupled from other matter, about 1 second after the Big Bang. These neutrinos have been streaming freely through space ever since. They fill the universe with a density of about 300 per cubic centimeter, though they're incredibly difficult to detect because they interact so weakly with matter. If we could detect the cosmic neutrino background, we would be observing the universe as it was at 1 second old, long before recombination. We would see through the photon barrier, glimpsing the Quark-Gluon plasma era, the Nucleosynthesis era. Unfortunately, these neutrinos are low energy, and no current technology can detect them. Future experiments may succeed. Gravitational waves, ripples in spacetime itself, were created during inflation and possibly earlier. These primordial gravitational waves should also fill space, forming a stochastic background. Unlike electromagnetic radiation, gravitational waves pass through matter almost unimpeded. They have traveled unscathed from the earliest moments. Detecting primordial gravitational waves would be revolutionary. They would carry information about the inflaton field, about quantum gravity, about the Planck Epoch. Current gravitational wave detectors like LIGO and Virgo are not sensitive enough, but future space-based detectors might detect them. These elusive messengers, neutrinos and gravitational waves, are windows into epochs before recombination, into the first seconds after the Big Bang, into the birth of time itself. They complement photon observations, extending our view deeper into the past. We have journeyed from the Planck Epoch at 10 to the minus 43 seconds, through the Quark-Gluon plasma, through nucleosynthesis, through 380,000 years of opaque plasma. We witnessed recombination, the dark ages, cosmic dawn. We saw the first stars ignite, the first elements forge, the first galaxies assemble. We watched reionization transform the universe from neutral to ionized. We observed the cosmic web mature, filaments channeling gas toward nodes, clusters forming at intersections. We traced star formation through its peak during cosmic noon and its gradual decline. We followed the chemical enrichment of the universe, from primordial hydrogen and helium to the rich abundance of heavy elements that enable planets and life. We arrived at the present day, 13.8 billion years after time began. This is the story of time, the story of how the universe evolved from an inconceivably hot, dense, uniform state to the vast, cold, structured cosmos we inhabit. It's a story written in physics and mathematics, confirmed by observations, refined by decades of scientific effort. But it's also a story of transformation and emergence. Simple initial conditions, quantum fluctuations stretched to cosmic scales, give rise to astonishing complexity. Hydrogen and helium become stars. Stars become heavy elements. Heavy elements become planets. Planets become life. Life becomes consciousness. Consciousness asks about origins. The birth of time is not just a story about physics. It's the story of how the universe became capable of contemplating itself, how unconscious matter organized into patterns complex enough to ask why they exist. We are time's witnesses, observing its unfolding, tracing its history.